Okay, and okay, so I'd like to introduce our speaker for today. This is Erin May. Let me bring up the bio here that I've now lost. Sorry about that. Okay, Erin May. Erin May is a postdoc fellow at the Johns Hopkins Applied Physics Laboratory. And prior to this, she obtained her PhD from the University of Michigan in 2019. She is primarily interested in the observational characterization of exoplanets. Her work encompasses ground and space-based observations, as well as 3D modeling of exoplanetary atmospheres. Currently, her research is heavily focused on a uniform reanalysis of Spitzer phase curves to uncover underlying population level trends. And her talk today, as you can see, let me just check that to make sure. There we are. Exoplanets, planetary exoplanet, Spitzer's exoplanet legacy, population trends from phase curve observations. Okay, so take it away, Erin.
Great, thank you. Thank you for having me today. So yeah, I'm Erin May. I'm a postdoc at Johns Hopkins Applied Physics Lab in Maryland. We are associated with Johns Hopkins, but we are a separate institution. And I'm going to talk to you today about observations of phase curves with Spitzer, primarily looking at how we can get beyond the noise to start looking at population trends and different parameters derived from phase curves so we can understand more about the circulation and atmospheres of these hot Jupiter planets. I'm going to start with some introductory level material for those that are either new to exoplanets, new to phase curve observations, new to anything that I'm going to talk about. So if you are an expert in any of the categories that I listed, feel free to take a bathroom break or go get more tea or coffee while I go through these first few slides and join back with us in maybe like 5 to 7 minutes. Everyone else in the room who doesn't consider yourself an expert in any of these fields, please feel free to stop me and ask questions during the beginning part, because I want to make sure everyone is on the same page as we move into some of my results and what I've been working on. What I like to start with is kind of an overview of a few really exciting things that Spitzer's been involved with exoplanets, not necessarily related to what I'm working on, because I found that a lot of people who aren't in the field of exoplanets actually did not know that Spitzer dedicated so much time to studying exoplanets, not only with phase curves, but also with a variety of methods. Overall, Spitzer has been wildly successful with exoplanets, more so than I think we may have expected when we started using the telescope. The first thing I want to highlight is that Spitzer was responsible for the first spectra of extrasolar planets. There were 2 planets that had spectra that came out at around the same time. This was HD 209-458b and HD 189-733b. These were 2 of the first transiting planets. I know some people in the call's favorite planets because of their history, but there were secondary eclipse observations of them back in 2007, and at first glance, these spectra may look kind of noisy, but they are really the first spectra we have of a planet outside of our solar system, and there were potential molecular signatures detected here. So it was really exciting and kind of laid the groundwork for what Spitzer was going to become for exoplanet science. The next thing I want to highlight is that Spitzer is responsible for the first map of an exoplanet. This is also HD 189-733b, and this used the technique called eclipse mapping. So that could be a whole talk on itself, just eclipse mapping. But the idea is that as the planet crosses behind the star, each new time point in your spectrophotometry is slicing off another small chunk of the planet. And then as it comes back out from behind the star, each new point in time, you're getting more slices of the planet. And you can build that up to a map of what the planet looks like. And the last thing that I want to highlight that Spitzer has really helped the field of exoplanet science with is that Spitzer was monumental in the confirmation of 5 of the TRAPPIST-1 system planets. I love this little Google Doodle of the system because it kind of highlights just how exciting this was. When you're confirming planets, you need to look at them in a bunch of different wavelengths to make sure that it's not a false positive. And Spitzer helped with that for 5 of the planets in the system. And this is a system of 7 planets, more or less Earth to Neptune size, with 2 or 3 of them in the habitable zone, depending on how you count what habitable means. So outside of all of these really exciting firsts that Spitzer's been involved with, Spitzer also observed nearly 60 phase curves of 31 different exoplanets during the warm mission. So this is after Spitzer ran out of coolant, and Spitzer wasn't able to observe at as long of wavelengths anymore, but it was still just as useful at some of the shorter wavelengths. These 60 phase curves total over 3,000 hours of observations, which is a significant number because that corresponds to about 10% of the primary JWST mission lifetime. There's no way we're going to re-observe all of these planets with JWST because we're not going to dedicate 10% of JWST time to phase curves as much as we might want to. And even if we were to dedicate that amount of time, we're not going to go back and re-observe most of these planets. So Spitzer is going to remain an absolute treasure trove of exoplanet data because not only did it observe all of these phase curves, it also observed a lot of eclipses and transits individually. So as we move into the era where we're going to be getting spectroscopic phase curves, more precise phase curves with JWST, we can't forget about Spitzer and all of the information it is continuing to teach us and will continue to teach us throughout the JWST era. So I've been talking about phase curves and eclipses and transits. So I want to talk a little bit about what they are and what we learn from them. I'm specifically focusing on transiting planets because that's the primary method that we've used to characterize exoplanets so far. There are various methods that exist and are upcoming to study non-transiting planets, but Spitzer didn't use them, and so I'm not really going to talk about those here. So if you're sad that I've forgotten your favorite method here, that's the reason why. So first, I'm going to highlight secondary eclipses. This happens when the star occults the planet, or the planet's passing behind the star. Just before secondary eclipse, the total amount of light that we're getting from the system is the starlight plus the emission from the day side of the planet. When the planet crosses behind the star, all we're observing at that point is the star itself. So we can measure the difference between out of eclipse and in eclipse to determine the day side flux of the planet. And we can convert that then to temperature for the day side of the planet. If we look at just a little graphic of what a phase curve looks like down here, where time would be along the x-axis and relative flux on the y, this small little dip here is what a secondary eclipse would look like. We also have a transit, which happens when the planet occults the star or passes in front of the star. And then in this scenario, what's most important is area ratios. So the size of the planet compared to the size of the star. The bigger the planet, the more light it's going to block out from the star. And so the depth is mostly to first order proportional to the planet to star area ratio, not flux ratio, sorry. In addition, some of the starlight is going to pass through the planet's atmosphere and interact with gases and molecules that are present in there. And so there'll be a slight variation on the exact transit depth depending on how much interaction occurs between the starlight and the planet's atmosphere. Sometimes it's absorbing more light, so we end up having a deeper transit because more starlight is missing. Now we can also, when we observe a phase curve, we're also seeing the night side of the planet at this point in time. And having the baseline of the phase curve observation of just the star when the planet's in eclipse allows us to use the transit point of time to measure the night side emission for the planet. This is most important for really hot planets that have larger planetary emission where we can actually detect it just outside of transit. Now, in between secondary eclipse and transit, the planet is rotating and orbiting the star. For tidally locked planets, that means over the course of one entire orbit, we're going to see every single side of the planet. These observations are called a phase curve. And there's a few different things that we can measure and learn about from a phase curve. The first is a phase amplitude, where we measure the peak amount of flux that we receive from the system, which usually occurs just around when secondary eclipse happens, and compare it to the minimum amount of flux that we receive from the system, which usually occurs right around when transit is, when we're getting the night side of the planet. And the difference between these two is the amplitude of the phase curve and tells us about how heat is transported around in the planet's atmosphere. If you have a really high amplitude, that tells us that there's not heat being transported from the day side to the night side. But if it's a fairly flat phase curve, that tells us that the planet is fairly uniform and that heat is very efficiently being moved from the day side to the night side of the planet. With a phase curve, we can also measure the hotspot offset, which is a measurement of when the peak of the phase curve happens compared to the middle of secondary eclipse. If the day side of the planet was the hottest hemisphere of the planet, this would occur right in the middle of secondary eclipse, because we would be, if there was no star there in the way, seeing only the day side hemisphere at that point in time. But these hot Jupiter planets in particular have really strong winds that are blowing heat off of the day side to the night side, and also shift the hottest hemisphere of the planet slightly away from just the day side of the planet. And we can measure just how much it shifted by measuring the peak of the phase curve and where that occurs. And this tells us things about the strength of the winds and circulation of the atmosphere as well. Transit is occurring at what we call a phase of 0 or 1, and a secondary eclipse generally occurs around a phase of 0.5. So the reason that we're generally making these observations with Spitzer is that planet emission generally peaks near-ish the Spitzer IRAC wavelengths. On the right, I'm showing you a 1500 Kelvin black body, which is approximately the temperatures that we're observing at with Spitzer, compared to the 4 Spitzer IRAC photometric channels. Now, when Spitzer ran out of coolant and we moved to the warm Spitzer mission, we no longer could observe with channels 3 and 4, but we were still able to continue observing with channels 1 and 2. Throughout this talk, I'm going to try to be very clear and say channel 1 and 3.6 micron together. So if you're not familiar with the terminology, you know at least what I'm talking about. But channel 1 refers to 3.6 micron observations, and channel 2 refers to 4.5 micron observations. Generally, channel 2 observations are a little bit more well-behaved, and I'll talk about that throughout the rest of the talk. On the left here, I'm showing planet equilibrium temperature on the y-axis compared to planet orbital period. The points are scaled based off of the size of the planet, so the larger circles are larger planets. And the color is just also equilibrium temperature for aesthetics, I guess. But these stars are highlighting the warm Spitzer phase curve targets that were observed, so approximately 31 targets in total. And what I want to point out is that we primarily observed hot Jupiters with Spitzer. It's kind of hard to tell with the stars sitting over the points, but most of these are approximately Jupiter sized, and they're also fairly warm and very close to their stars. All of these planets are on orbital periods of less than 5 days, and most of them are on orbital periods of closer to 2 days or less. And they're also mostly above around 1100 Kelvin equilibrium temperatures. Because these are hot Jupiters close to their stars, we expect them to be tidally locked. So there's going to be a significant difference between their day and night sides to a level that we'll be able to measure it with Spitzer. These hot Jupiters also likely have strong winds in their atmospheres because of this day-night forcing that's happening. So they also should have phase offsets that are at measurable levels from Spitzer. So all of this really points to hot Jupiters and Spitzer seeming like they're a great pair, and it's the perfect telescope to go out and observe all these planets so we can learn all about their atmospheres. But unfortunately, Spitzer was, like most telescopes, not designed with exoplanets in mind. Spitzer observations, the raw flux is often, to put it nicely, a mess. I'm showing you here what are 2 phase curves, and I've redacted the planet because it doesn't matter at this point. But on the left, you can see the flux is kind of this wavy, weird pattern. Transit should be happening somewhere around an orbital phase of 1, and you can see a couple points decreasing there. But if we didn't know that's when transit would happen, you kind of would that actually look like a transit to us? So there's one reason why this generally happens. It's that, not generally, just one reason why this happens. Spitzer has very strong systematics. Spitzer wasn't designed to take the high precision, long time baseline observations that we need to do phase curves. And the reason this is a problem is because of this systematic specifically called intrapixel sensitivity variations. So channel 1 and channel 2 is 3.6 micron and 4.5 micron are dominated by this effect, where the measured flux depends strongly on the location of your centroid. So if you're an observer in the audience, you'll be familiar with the concept of flat fielding, where every pixel itself has its own sensitivity. And you have to take a flat field to measure which pixels might be responding more strongly or weakly to the same amount of flux, a uniform illumination. With Spitzer, what happens is within a single pixel, there's variations in the sensitivity. So, your aperture is generally around 2 pixels wide, but the amount of flux you measure matters where the middle of that centroid, your PRF, falls on your pixel. In addition to this intrapixel effect, where you're going to measure different flux depending on exactly where a star falls within a single pixel, the shape of your PSF or PRF also changes as the centroid drifts away from the center of the pixel. So in the center of the pixel, the starlight should be fairly spread out in a circular pattern, but as you move to the edges of the pixel, it stretches out to an oval in either direction. This is important because aperture photometry is generally just assuming a circle for your aperture. And for Spitzer, it's generally true that you get the best performance if you apply a constant aperture size throughout your data extraction. But if you apply a constant aperture size and your centroid is drifting away from the center of the pixel, you end up missing some flux in some of your frames. This is a relatively small effect compared to the intrapixel sensitivity variations, but it has been shown that for some data sets, it's actually very important to include this in our detrending because it can slightly improve the precision of our final phase curves. So with these two effects, we have to remove them from our data so we can get to the underlying astrophysical signal. And all of this happens within an MC. So to go from this bad data to our quote unquote good reduced data, we have to remove both this intrapixel effect and, if it's strong enough, this PRF effect. So we have this raw data, which looks very bad on the left. And within our MCMC, our first step is to select an astrophysical phase curve model within the bounds of our priors. We generally use flat priors that are uniform and fairly uninformative. There are a few parameters that we know very well, like the orbital period, for example, that we can constrain. But things like the phase curve amplitude and offset, those are free to vary very widely. After we select this astrophysical phase curve model, we fit a polynomial form to the Gaussian width trends, where the Gaussian width refers to the shape of this PSF, so how stretched out it is in both directions. Then we take the residuals between our models and grid them spatially to create this pixel map, which we then interpolate back onto the centroid locations of our data and use that to detrend all of these strong intrapixel variations. So in the end, what we're left with is this raw data that is fit by a map that's interpolated onto our data points, any other systematics like this PRF effect, and then our astrophysical underlying model. We can then just divide out that systematic model and we're left with data that looks like a phase curve. I want to note that this method is essentially self-calibrating the data, so it relies on there being well-behaved observations that are going to revisit the same location on the pixel multiple times. If you don't come back to the same location on the pixel, it's hard to know what percentage of the flux measured at that position is a result of the astrophysical signal or a result of the systematics themselves. So we looked at this effect of how to best remove these systematics when we have a strong PRF effect and this intrapixel effect in our 2020 paper. And we found that the PRF Gaussian widths and the centroids are highly correlated, which is what we would expect. If you're moving from the center of the pixel, your centroid is drifting and your PRF is stretching out into an oval. So we would expect there to be some correlation. We found that this there ends up being these sinusoidal repeating features on the order of about 10 seconds in this Spitzer data. This is occurring at both 4.5 and 3.6 microns in both our centroids and our Gaussian widths in both dimensions. Now, this is fine in general, because if you look more closely at this plot of relative centroids versus relative Gaussian widths over here on the left, you can see there are subtle differences between the two. However, many Spitzer data sets are composed of tens of thousands, if not hundreds of thousands of exposures, and that can get computationally expensive to analyze. So some groups end up temporally binning the data to make it a more manageable size. You can imagine if we started temporally binning this plot of centroid and this plot of Gaussian width, it would be flattening out and we would lose the subtle differences that are showing up between the two, allowing us to fit them as independent functions. So what happens is when you bin the data, temporally bin the data, you remove the features that allow you to independently fit the two, and you can get inconsistent and degenerate phase curve fits. This is a figure, a part of a figure from May and Stevenson in 2020, where we showed the effect as applied to 3 different possible phase functions. So sinusoidal, spherical harmonics, and Lambertian. On the top, we don't include that PRF detrending, and on the bottom we do. And for every panel, we progressively bin the data in time. So that's what each of these different color lines are that you can see on the bottom. When we're including this PRF detrending, in addition to the standard mapping technique, the phase curves kind of drift away from the initial no binning result. And it's not clear what the true best fit is. So naturally, when there's some degeneracy, we want to be able to find a way to hold one side of it constant so we can constrain the other side of it. So to do this, we generated an up-to-date intrapixel sensitivity map, which is expanded on a map that was made in Ingalls et al. In 2012. The notable difference being that we used more calibration data, around, I believe, 3 million calibration frames at 4.5 microns. And we also applied the same exact data reduction techniques as we do in our Spitzer analysis pipeline. Our map here uses, in particular, a different centroiding method than Ingalls et al. 2012, which allows us to apply it directly to our Spitzer analysis pipeline. The map I'm showing you here, so these are just it's subpixel units on both axes with normalized flux as our color here. And this black square region is what is typically referred to as the sweet spot for Spitzer observations, where the flux typically doesn't vary too much as long as you stay kind of in the peak of sensitivity here. The part on the right-hand side was published in May and Stevenson 2020, and this part on the left is an extension to the map that's going to come out and be added to the POET Spitzer pipeline with our next publication that is in prep and soon to be submitted. So when we have this map, we can divide it out from our data in advance, leaving only the astrophysical signal behind, and occasionally other weirdness, but we can deal with that as it comes. Now this is only the 4.5 micron map. And we found there's some additional difficulties when trying to do a similar technique for the 3.6 micron data. So for all of this calibration data, it was easily dividable up into 3 distinct points in time where the data was taken. So I'm showing here difference maps between those 3 points in time. Each one is a different 2 sets of time subtracted, and it's plotted as the normalized map difference in percent. This is for 4.5 micron, and you can see it's kind of just looks like, for the most part, random noise, which is good. This is telling us that there's no time variability happening in the 4.5 micron calibration data. But at 3.6 microns, or channel 1, what we found is, and I'll point out, these are the same color bar scales. There was significant time and spatial variability in the sensitivity, intrapixel sensitivity, so we weren't able to generate a fixed sensitivity map that we could apply to the data in the same way. Now we have some paths forward to try and create one anyways, in order to determine if this variability is intrinsic to the channel itself or perhaps just the calibration star itself. So you can stay tuned for some results in the coming years from our group on trying to improve channel 1's data reduction techniques. So takeaway number one from all of this is that we've concluded that Spitzer data should not be temporally binned. Even though the data sets can be quite large, it's really important that we don't remove the underlying systematics that allow us to detrend them without degeneracies. So because of this, we did develop this new detrending tool for 4.5 micron Spitzer data. And if you're interested in phase curve or just transit eclipse observations, I really encourage you to take a look at this paper and use our technique. And I have put an asterisk next to Spitzer. This result is obviously very specific to Spitzer observations, but I think it's really important we consider this when we're moving to other data sets as well. We shouldn't be temporally binning our data until we're really sure we understand all of the time variable systematics that might be affecting our data results. This map we first applied to WASP-43b because WASP-43b is one planet where we found that different groups looking at it ended up getting different results. And part of that is because some groups do apply this temporal binning. So for WASP-43b, we found that our new results ended up being more consistent with 3D model predictions. And it was an interesting case study because it really is this prime example of how data sets that look well behaved to the initial scan of the data, they can really be just as problematic as data sets that don't necessarily look well behaved right at the beginning. So at the bottom, the panel that's highlighted in yellow, this was our new analysis of this phase curve. We ended up getting a higher night side flux than the original Stevenson et al. Result, more in line with two of the following studies on it, and more in line with 3D model predictions. So these are models from Roman et al. In 2021, and I want to focus on the bottom panel here, where I'm showing the phase curve amplitude in the maximum minus minimum over maximum compared to the planet irradiation temperature, which is just a square root of 2 compared to an equilibrium temperature. This old WASP-43b reduction is this Stevenson et al. 2017, and our new WASP-43b reduction using our fixed sensitivity map brings it more in line with these 3D model predictions of what the phase curve amplitude should be for a planet with that gravity, assuming that it's cloudy. There are some subtle differences that show up as well between our phase curve amplitude, our phase curve offset compared to all three of the previous analyses. But I'm not going to talk too much about that now, and I encourage you to go read the paper or reach out if you have any questions about that. But overall, the most important takeaway from the slide is that data reduction is a complex process. And in order to really make the best use of all of the Spitzer data we have, as well as upcoming JWST data, we need to be really careful to ensure that different systematic models end up converging to the same results. And this is a major reason why many groups are actually moving to these multiple independent reductions of data sets to ensure that there's consistency in our results. But with that in mind, and the fact that many of these previous Spitzer reductions have used specialized methods for each planet, we've decided that we wanted to try to do a uniform reanalysis of all of the existing Spitzer phase curves with special care given to each data set as necessary in order to try and mitigate some scatter and astrophysical trends. You can see that if we ignore the WASP-43 point, which we had redone at this point, not a lot of these points don't really line up well with some model predictions. And there's various reasons for that, but we're concerned that the scatter might not be entirely astrophysical. Some of it might be due to underlying systematics and different data reduction methods between different groups, resulting in different answers. So our goal is to perform this uniform reanalysis to mitigate some of this astrophysical scatter and start to look for these underlying trends with as uniform of a data set as possible. So to start, we want to first go through and analyze all of the phase curves that haven't been studied yet. And the first one I want to highlight is WASP-76b, which has been quite the hot topic recently, both because of its temperature and because it's a great target. There have been a lot of papers coming out in the past few months and years studying this planet with a variety of methods. So WASP-76b is an inflated ultra-hot Jupiter. Inflated just means it has a larger radius than we might expect for a planet of its mass. And ultra-hot, the exact cutoff for what is hot and what is ultra-hot depends on who you ask, I think. But WASP-76b in general has a temperature of around 2200 Kelvin. There's been a lot of ground-based observations recently that have detected, among various other things, iron condensation on the night side of the planet. And this is where this idea of iron rain has come from. This is a beautiful artist's rendition of clouds condensing on the night side. This idea of singing in the iron rain on WAS-76b. And unfortunately, it did not make it very far in the ExoCup this year, much to many of the people who have studied its sadness, because it's a great target for continued study. I've listed a few papers there if you want to go look at these ground-based observations. I'm not going to talk about them. If I missed your paper in that list, I'm sorry. There's a lot of them, and it's hard to keep up and keep things updated sometimes on this specific planet. So the reason that this is an exciting planet for us to study is that theory suggests that it should have a hot internal adiabat in order to inflate the planet to its large radius. This should most strongly affect the night side of the planet, where we would expect it to be cooler. So if it was hotter, it would be much more evident to us. As I mentioned in the beginning, phase curves allow us to study the night side of the planet because we have that baseline of in eclipse, so we know what the stellar flux is, and we can use that to determine exactly how much night side flux we're receiving from the planet. Now, before I get into the results for this, I want to note that this is a co-first author paper. So if you have questions about how to cite it properly in LaTeX, please send me an email and I'll send you a little snippet of LaTeX code for adding it as a citation in your papers so that in text it shows up properly. So with all of that, I'll want to talk briefly about the data. We observed 2 phase curves at 3.6 microns and 1 at 4.5 microns. So there were 2 at 3.6 microns because of some issues with the scheduling, not because it's any more special. But this ended up being a good thing because, as I've mentioned, 3.6 micron or channel 1 data is generally less reliable maybe, or just more annoying to detrend because there's a stronger intrapixel effect there. So on the left, I'm showing our reduced phase curves. So these have the systematics removed for 3.6 microns for both visits with the residuals on the bottom. We fit these jointly, so they had the same, they required to have the same phase curve parameters, but different maps, intrapixel maps, because of what I talked about before, whether we expect there to be this time variability and the sensitivity there. There were some minor difficulties reducing this data I'm not going to talk about, so please go read the paper if you're interested. And then for 4.5 microns, we were able to use our fixed sensitivity map, but WASP-76 has a nearby companion, so we had to apply 2 maps, one for the primary target, our primary star, and one for the stellar companion. That was with the centroids shifted to the correct relative location of the 2. So what I'm showing on the right is our reduced 4.5 micron map. At the top is in orange is our primary map for WAS-76, and in purple is the companion map. And you can see it has a much lower, much weaker effect because the companion is about 10 times fainter than WAS-76. And then there's a slight linear temporal ramp that we generally need in most data sets. Overall, this resulted in a fairly clean, reduced phase curve. Both the main target WAS-76 and the companion did overlap with our fixed sensitivity map. So none of this is self-calibrating. So it's really exciting that we've now seen this work in application to 2 completely different planets. Now, phase curves alone are great, but in order to really understand what's going on, we need models. In this paper, we ran a suite of models with the MIT GCM, considering both a cold and a hot interior, because remember, we're trying to understand if a hot interior is really necessary to explain the large radius of the planet. We also included 5 different drag strengths, and drag is induced in order to effectively change what the wind speed and circulation pattern end up looking like in the atmosphere. What we're looking at here are maps of the brightness temperature output from these GCMs, so longitude versus latitude. And then as we move from the top to the bottom, we're increasing the drag strength, which corresponds to a shorter time scale. And the left panel is our cold interior, and the right panel is our hot interior models. Overall, there are stronger winds in the cold interior models because there's more significant day-night forcing, which is driving this equatorial jet. And you can see that if you look at these top two panels, the color bars are slightly different, I'm sorry. But if you look at where the hottest region of the planet is compared to the small black dot, which is a substellar point, you can see that there appears to be stronger winds in the cold interior model. This isn't anything new or exciting. I just wanted to point it out when we start comparing it to our phase curves later. In general, we can characterize our weak drag cases where the timescale is greater than 10 to the 5 by having these strong equatorial jets that I pointed out here, which is where we appear to see more heat concentrated along the equator being blown from the day to the night side. But as we increase our drag to these stronger drag timescales, or tau less than 10 to the 5, we start to lose that strong equatorial jet and just have day-night flow moving away from the hottest side of the planet to the night side, not necessarily along this equatorial region. Again, this is nothing necessarily new or groundbreaking in these 3D models, but I wanted to point it out as a feature that we'll be able to compare to our observations. So we did find that surprisingly, the cold interior strong drag 3D models best matched the phase curve. Remember I mentioned that we expected there to be a hot interior because there's an inflated radius, and we thought that was necessary to explain the radius. But it turns out these cold interior models match our data better. So on the left, I'm showing our 3.6 micron data compared to post-processed phase curves of our hot interiors at the top and cold interiors at the bottom, and the different drag timescales as the different colored lines. So the purpley lines are our stronger drag cases, and the orange lines are our weaker drag cases. And then the same thing is being shown on the right for 4.5 microns. So I already mentioned that we did not expect the cold interior models to match the best, but that is in fact what the data shows, is that that WAS-76 likely has a colder interior than anticipated. And we also found that we needed strong drag models. So the purple lines generally match our data better. This is particularly surprising because some of the ground-based high-res observations, in particular, the first one, that Erin high-res observations that led to the iron rain, they require low drag in order to explain the change in iron abundance between the day and the night side along the evening terminator. But I do want to point out that even though the cold strong drag models do match our data better, they don't actually explain all of our phase curve parameters. So this is just, this is a plot from our paper where we're looking at 4 different phase curve parameters: the day side flux, night side flux, phase curve amplitude, and phase curve offset. And the horizontal shaded regions correspond to our measurements at 3.6 micron in orange and 4.5 micron in blue. And the x-axis here is drag timescale. So moving to the left is stronger drag, and moving to the right is weaker drag. And the model coloring is the same with these hot interior models as dashed lines and cold interior solid lines. So you can see from this that these stronger drag timescales do match our data better, as well as generally the colder interiors, but none of them match perfectly. In particular, the 3.6 micron data does not agree well with any of the models, but it's not really uncommon that we don't see great agreement between Spitzer observations and 3D models. And there's various reasons for that. You can blame both us observers and you can blame the modelers, depending on which side you're on. But we don't, there's nothing scary about the fact that our data and models aren't necessarily perfectly agreeing at this point. And some of the caveats for our models in this work are that the models are cloud-free. This is probably not an issue because we're looking at an ultra-hot planet, and we don't expect there to be a particularly cloudy night side here. These models are double gray, so that means there are essentially 2 wavelengths considered in the models. There's short wavelength optical and long wavelength infrared, and they have constant absorption coefficients for both of them. This is obviously not necessarily entirely physical, and models have shown that if you include more nuanced absorption coefficients, you can end up affecting your day to night redistribution. So that's something that we may want to consider in order to explain some of these observations. And then finally, the last caveat I want to mention is that our models here assumed a uniform drag timescale. And we do know that some drag is not spatially uniform. And for example, something I'm going to mention in a little bit, magnetic drag will likely be important for these hot Jupiters, ultra hot Jupiters, and that can be spatially dependent because that's going to depend on the ionization in your atmosphere. Now, I've mentioned all these modeling caveats. I do want to say that our 3.6 micron data, as I mentioned briefly before, was not entirely the most reliable result. So it's not necessarily just the fault of the models here that our models don't match the data. And some of the takeaways from this study of WASP-76 is that the lack of hotspot observation generally agrees with observations of other ultra-hot Jupiters, namely WASP-103 and WASP-18. As I mentioned, recent work suggests that these ultra-hots might have strong enough magnetic drag to explain the observations. This is recent work from Haley Belts in 2021. And I want to highlight this beautiful figure from her work showing that, again, these are temperature maps of the planet. As you move from no magnetic field in this left column over to a strong 30 Gauss magnetic field in the right column, and then the rows are just increasing pressure levels. If we look at this middle one, just focus there for a second, we can see when there's no magnetic field, you get that typical looking equatorial jet. And as you increase the magnetic field, you lose that equatorial jet because you end up having a strong due to strong ionization, you've had that strong magnetic field, and you can end up having flow over the poles and away from the day side instead of just along the equator. And the fact here is that this drag can be spatially dependent, depending on the temperature and amount of ionization on where you're looking at the planet. So I'd be very curious to have this looked into more as a potential reason why we're seeing that we need a strong drag on the day side of the planet, but many of these ground-based high-res observations are only requiring low drag to explain their observations. Finally, I want to point out that if our 3.6 micron data, channel 1, holds true, WASP-76b is one of the first planets where we have definitive evidence for day-side inversion transitioning to no night-side inversion. So from secondary eclipse measurements alone, there have been plenty of day-side inversions measured. But what's special here is the detection, confirmation of no night-side inversion in the planet's upper atmosphere. So the takeaway number 3 from this is that we need better models, and no offense to the modelers in the room. Phase curves are uniquely probing the day and night side and give us insight into the circulation, but many models are lacking necessarily the physics to match the data. Now, this is by design. 3D GCMs are expensive, and adding more physics makes them slower. We always need to make some assumptions, but future work will be considering additional physics and how that might better match observational predictions, not just for individual phase curves, but for trends overall. Next up, and what we're currently working on is to finish analyzing remaining unpublished Spitzer phase curves. So I'm showing the same plot I showed before with phase curve targets marked as these black squares. And now I want to highlight the ones that are currently unpublished from warm Spitzer. I'd say about half of the planets have unpublished phase curves, which is a significant number that still remain to be studied. In our upcoming work, we're looking at 5 of these, which corresponds to 8 phase curves. And the 5 planets we're looking at all have equilibrium temperatures of approximately 1300 Kelvin. So these are among the coldest that were observed with Spitzer. And this uniform temperature amongst them allows us to study secondary trends in the atmospheres. So we've effectively removed any trends due to temperature by just selecting these 5. I'm not going to linger on any one particular planet very long here, but I do want to just highlight that just like all sets of Spitzer observations, the data ranges from at first glance well behaved to what was Spitzer even doing, which is unfortunately the case for at least one of these targets. These figures are just showing the centroids in X and Y on the top bit of them, and then the raw flux on the bottom. If you want to look at these longer, the paper will soon to be submitted and showing up on an archive near you, hopefully in the next couple of months. We did use our fixed sensitivity map when applicable. Of course, there's always exceptions to our attempt to have as uniform of an approach as possible. First of all, being that there's currently no fixed map method for 3.6 micron data. As I've mentioned before, that's something we're hoping to develop in the coming years. But for now, we just use a standing mapping technique for 3.6 micron phase curves. For one of the 4.5 micron phase curves, it doesn't overlap with our current iteration of our fixed map at 4.5. This is something that, again, we're hoping to be able to expand our map more, and maybe we'll be able to reanalyze this in the future with our fixed map. But for now, we've just done it with a standard mapping technique as well. For WASP52B, the 4.5 micron phase curve had inconsistent PRFs. They kind of jumped around more than expected, and we found that using our fixed map required the addition of PRF to trending. Generally, when we use our fixed map, we don't actually need to include that because the calibration data kind of takes that into account already. But we believe it's because there ended up being these long stripes of centroids along the edges of a pixel rather than towards the center. WASP34B's 4.5 micron phase curve is my what was Spitzer even doing case. This is the longest phase curve observed by Spitzer, 4.5 days. And you can see again these long stripes of centroids that weren't revisited by the telescope. So it's hard to detrend them, especially when they don't overlap with our fixed sensitivity map well. Ch1B 4.5 micron was a well-behaved data set. It partially overlaps with our fixed sensitivity map, and our results ended up agreeing well with previous observation or previous reductions. And then WASP140B was generally well-behaved, even though it had these non-overlapping AORs or astronomical observation requests. They all overlapped with our fixed sensitivity map, so we were able to detrend it fairly well. Again, not going to focus too much on any single planet here. Our analysis was as uniform as allowed by the data. I do want to point out WASP140B, what we thought would be a great planet to include in our survey here. It is slightly eccentric, and there ends up being some oddities about where we measured the phase offset to be, potentially just due to the eccentricity of the planet. So we generally exclude it from all of our trend fitting that I'm going to talk about for the rest of this talk. So first up, we do find evidence for a trend of increasingly eastward phase offsets with orbital periods. To our knowledge, we don't have any model predictions about this yet, but I do know there are some modelers who are excitingly working on it now to understand why this is the case. On the top panel, we're just fitting a trend to the 4 remaining planets in our 1300 Kelvin survey. The flat blue line is a 0th order, just flat trend compared to a green linear trend. And we do find evidence that a linear trend fits better, but of course, this is heavily dependent on our single WASP34B observation. But if we look at the full population in the bottom, our phase offset has a much stronger linear dependence of increasing offset as the orbital period of the planet increases. So we're really excited to see what model predictions might explain this. But we are also excited that this trend appears not to just hold in the full sample, but also in our 1300 Kelvin sample, if you want to believe a 4-point fit. We also look at the apparent redistribution of heat around the planet compared to the equilibrium temperature of the planet. So I'm comparing this to models from Parmentier in 2021. So these thinner blue lines correspond to their predicted 4.5 micron emission, and the thicker blue lines correspond to the bolometric emission, with dashed lines being cloud-free and solid lines being cloudy. The first thing I want to point out here is that our sample spans a wide range here. So here's Ch1, WASP52, Ch2, WASP34, and WASP140. These are our 5 planets at around 1300 Kelvin. We span a very large range here, which tells us there's more going on than just temperature when we want to understand how redistribution is happening in the planet's atmosphere. I've also added this very tentative hopeful line here, where maybe we're seeing a population up above it where there's weak redistribution happening in the planet's atmospheres, and down below where there's stronger redistribution happening. But unfortunately, there's a lot of bias in the sample in the literature. We're not always sure which stellar parameters were used to calculate the day side temperature of the planet. So we can't make sure that we're using the same to calculate the equilibrium temperature, for example. So this is something that we'll be hopefully cleaning up over the coming years as we go through and perform this uniform reanalysis of all Spitzer data. One of the last things I want to talk about is this comparison of offset and amplitude to radiation temperature. And I did show a version of this plot before, but now I've added on our new sample. The models here are from Roman et al. In 2021, and the colors correspond to gravity. First, I want to point out that our offsets, measured offsets from both our new sample and the literature don't agree well with models. There's in general this systematic offset where if we shifted all of the measured values up, they would agree well with models. So we're very curious to understand what's going on there when we start looking at adding additional model or additional physics into our models. The amplitudes of our new data agree well with these model predictions. So our new data are these solid points on the bottom. And it suggests that 2 of the planets are potentially clear and 2 of them are potentially clear on the bottom, sorry, and cloudy on the top. But there are these potential inconsistencies in literature values for the rest of them. And that's again something that we'll be cleaning up in the future as we work to reanalyze some of this data. I also want to point out that there's maybe some trend happening here in offsetting gravity, where these 2 planets with higher gravities have these westward offsets, and the 2 planets with lower gravities have eastward offsets. So we're maybe grasping at straws here, and we're hoping this trend holds when we start to reanalyze other planets. But if we look at offset versus gravity and color-coded now by equilibrium temperature, we can maybe add some make-believe trend lines here, and we're excited to see if this holds as we continue working on the data sets. So my last takeaway is also kind of the same as a previous takeaway, is that we need a uniform reanalysis in order to really understand the trends going on in these hot Jupiter atmospheres, because these different data reduction methods can and do result in different answers, and we want to make sure we're using the same one for all of them. I'm going to end with what I like to do with this talk and a tweet. So if you walk away only remembering one thing, or if you just tuned in now, I just remember that current scatter and phase curve derived population level trends might not be astrophysical, it might be astrophysical, remains to be seen. But our team is working on models with additional physics, as well as a uniform reanalysis of all of the Spitzer phase curves to mitigate some of this and better understand what's going on in hot Jupiter atmospheres. So stay tuned for my work over the next, from our team over the next few years. I'm really excited to see what comes out of this, and I'm happy to take questions.
Thank you, Erin. That was a great talk. Okay, we have a couple of hands raised, so let's go with Hannah. You're allowed to, you're able to unmute yourself.
So for the phase curves that you showed, which had kind of troubles, is that because they're not landing on a particular pixel, or they're going across multiple pixels? What aspect of those kind of distributions that we were looking at is it that those observations really just didn't hold with?
Yeah, so great question. All of the above. So WASP-34b, it was the longest phase curve observed by Spitzer. Spitzer actually ended up having to do a data downlink in the middle of it because of the amount of data. It was also, I believe, the last phase curve observed with Spitzer. So Spitzer, I think, was just doing some weird stuff at the end of life. It became harder for the telescope to remain pointed at directly the same region. So as a result, you end up with, when you see these long stripes on these centroid maps, it means the telescope was drifting. And when it's drifting, it doesn't revisit the same location, so it becomes harder to remove some of these intrapixel effects. Generally, our fixed sensitivity map helps with that, but WASP-34b was a special case because the data was just not good to begin with, unfortunately.
Will James Webb suffer with this, even though it's not doing as many phase curves as Spitzer did? Is there a chance that we'll see this kind of effect appear on the pixels, or if there's drifting involved for phase curves with Webb? I
think one of the instruments has the same type of detectors as Spitzer IRAC did, in which case probably, and hopefully we can get that figured out fairly early on in Spitzer. Otherwise, I think it just remains to be seen, and we just need to be really careful going in to make sure we understand the systematics and we're not accidentally, smoothing over them or something.
Awesome, thank you.
Okay, are there any other questions? Okay, Haley.
Hey, Erin, great talk. I'm wondering if, so at the end when you were talking about the different trends of especially like hotspot offset as a function of temperature and things like that, I wonder if you've considered thinking about the variability of hotspot offset, especially in the higher temperature planets where you definitely are expect to maybe see magnetic effects causing variability in that hotspot.
Yeah, again, great question. Unfortunately, many of these planets only have one phase curve observed in a given channel. Each phase curve does typically have 2 eclipses in order to have leverage arms for reducing the data. But those would be so close together that I don't know that we would expect to see the variability between the 2. I think that's maybe a more important question when we start getting JWST data if we take repeated phase curves of any of the targets.
Very cool stuff. Thank you.
Okay, and Guanwei Fu, sorry if I'm mispronouncing your name. Did you have a question?
No, that was not a question. I think I sent a clapping emoji.
No problem at all. Thanks. Okay. Okay.
But great talk though.
Oh, yes, it is. It is clapping. Nice, nice. Okay. Okay, so we're getting close to the end of our seminar. Thanks everybody for tuning in. We have these every month, first Tuesday at this time. And if you're interested in speaking at a future webinar, let us know. Contact anyone on the Leadership Council with your questions. And thanks all. Thanks everyone.